Hello everyone. This video is for introducing the paper Accelerated Speculative Sampling based on Tree Monte Carlo, which is published on ICML 2024. We first briefly introduce the motivation behind conventional speculative sampling. Autoregressive language models generate text sequentially, predicting the next toucan based on the previously generated toucans. While this autoregressive approach has proven to be highly effective in modeling complex distributions, it also comes with a significant computational cost. Each toucan generation requires a forward path through the model, which can be time-consuming, especially for large, state-of-the-art models with billions of parameters. Now, imagine a scenario where all the input toucans are known in advance. In such a case, we can leverage the power of modern hardware, which is well-suited for parallel computation, to perform a single forward pass for multiple toucans. This is much faster than performing multiple forward passes for individual toucans, as the time difference between a single forward pass for multiple toucans and a single forward pass for a single toucan is not significant. With a single forward pass, we can obtain the output distribution for all toucans and then sample the output toucans accordingly. However, a natural question arises: where can we have the toucans as input before generating them? This is where the concept of a draft model comes into play. We use a draft model to provide these input toucans. Here's the algorithm flow illustrating the process based on the draft model. First, the draft model generates toucans normally, providing us with draft tokens. It's important to note that these draft tokens are not the final output tokens. They serve as a reference. We then perform a single forward pass using these draft tokens as input. After sampling the final output tokens, we need to validate them. If all the output tokens match the draft tokens, the validation is successful, and in this example, all 4 draft tokens are accepted. However, if even only one token doesn't match, all the subsequent draft tokens must be discarded. In this case, only 2 draft tokens are accepted. A natural question that arises is how to maximize the average number of accepted draft tokens. This is where the advanced Monte Carlo methods become necessary. The basic idea here is maximal coupling. Let's consider 2 probability distributions, target distribution P and draft distribution Q. The goal is to sample from the distribution P while leveraging the samples from distribution Q to accelerate the process. Here's the intuition how it works. We first sample a point from the area under distribution Q. If the point lies within the overlapping region, shown in red, we accept the point as a valid sample from the distribution P. However, if the point falls in the non-overlapping white area, we need to sample another point from the non-overlapping region of the distribution P. With this sampling process, it's guaranteed that the output point is uniformly distributed in the area under P. The acceptance rate for this process is equal to the size of the overlapping area between the 2 distributions. In other words, the more similar the distribution P and Q are, the higher the acceptance rate will be, leading to a more efficient sampling process. The concept of maximal coupling lies at the core of speculative sampling. In this context, we have 2 distributions: the targeted distribution, which represents the distribution of the original model, and the draft distribution, which corresponds to the distribution of the draft model. We anticipate the draft model to produce a distribution that is as similar as possible to the target model's distribution, thereby increasing the overlap between them. Once we have the target and draft distributions, we can compute the maximal coupling. Let's consider an example with a vocabulary of 3 possible tokens, A, B, and C. The matrix shown here shows the solution to the maximal coupling problem, which will be used by the speculative sampling. Speculative sampling allows us to achieve acceleration while maintaining two important properties. First, retraining isn't required. We can use a draft model to accelerate existing large language models without additional training on large language models. Second, the quality of the generated text isn't affected. By leveraging the maximal coupling approach, we ensure that the output distribution remains the same to the original model. However, a natural question arises, can we make this process even faster? An intuition is that the vanilla speculative sampling approach applies maximal coupling in the token space, but the output of large language model is a sequence in a tree space. What if we could take a step further and consider the whole generation space? This is where our novel approach, accelerated speculative sampling, comes into play. Before we dive into the details of our new method, it's important to understand why the conventional speculative sampling approach is suboptimal. Speculative sampling applies maximal coupling incrementally for each new token. It doesn't take into account the overall structure of the generated text. And the final coupling is the direct product of maximal coupling for each token. The table left shows an example of coupling achieved by conventional speculative sampling when there are two draft tokens. However, the maximal coupling within the entire output space is not simply the product of maximal couplings in each token space. Therefore, speculative sampling is not optimal when the number of generated reference tokens is more than 1. Given that speculative sampling is suboptimal, this toy example illustrates an example of how we can manually derive the optimal coupling. By formulating the problem as a simple linear program, we can obtain the optimal solution. Let's observe the difference between the optimal coupling and the one obtained by speculative sampling. The optimal coupling shifts the probability mass within the red circles. This kind of shift is not considered by speculative sampling because when calculating the coupling for the second token, the probabilities related to the first token are computed through a direct product and then fixed. By performing a global maximal coupling, we can achieve better results. In this example, the light green color indicates accepting one token, while the dark green color represents accepting two tokens. Therefore, the optimal coupling can accept more tokens on average, resulting in higher efficiency. What's particularly interesting is that this improvement is almost free. We haven't introduced any new information or made additional calls to the model. The acceleration solely comes from better utilization of the information we already have. We can view the problem from another perspective. All possible outputs of a large language model form a tree structure, and the probabilities can be associated with each node in the tree. Speculative sampling in its current form only deals with one layer of this tree at a time. It first processes the coupling for the first layer and then moves on to the next layer. This approach hinders the realization of a true maximal coupling across the entire tree. In contrast, our proposed method, accelerated speculative sampling, considers this tree as a whole, leading to higher efficiency. However, to achieve this, we need appropriate mathematical tools to handle the tree structure of the generative space of large language models. To convert our intuition into a solid mathematical framework, let's first review conventional Monte Carlo methods. In conventional Monte Carlo, we have a probability distribution P defined over a space X. The goal is to design a sampler that maps from a random source space B to X, such that when we sample from the distribution PB, the output of the sampler follows the targeted distribution P. Now let's introduce our novel concept, tree Monte Carlo. Similar to the conventional Monte Carlo, tree Monte Carlo takes a tree distribution P defined over a tree space X. The goal is to design a sampler that maps from a randomized source space B to X, such that when we sample from the distribution PB, the output of the sampler follows a subdistribution P' of the target distribution P. The most interesting and unique aspect here is the concept of subdistribution. In a tree structure, there is a natural partial order among the paths. This partial order naturally induces a partial order among the probability distributions defined on the tree. We define a subdistribution P1 to be less than or equal to another distribution P2 if two conditions are met. First, the probability on each node in P1 is less than or equal to the corresponding node in P2. Second, for all sibling nodes, the probability ratio is preserved between P1 and P2. I wish to clarify that in this visual representation, the number on each node represents the sum of probability of the node itself and all its child nodes. Therefore, the number on the root node is always 1. This is because the root node represents the entire probability space, and the sum of the probabilities of all possible outcomes must equal 1. In the example on the left, note that the sum of the probabilities of the 3 bottom leaf nodes does not equal to the probability of their parent node, which is 0.5. This implies that some probability density is concentrated on the parent node itself rather than on its child nodes. It's also important to note that when a node in the visual representation doesn't have child nodes, it doesn't necessarily mean that the tree structure itself lacks child nodes at that point. Instead, it indicates that there is no probability assigned to those child nodes. Intuitively, a subdistribution contains less information compared to the target distribution, but it's compatible with the target distribution due to the preserved probability ratio among sibling nodes. With subdistribution defined, we can introduce the concept of subsamplers, which opens up new possibilities for ensuring that the generative process on the tree space follows the desired distribution. A subsampler intuitively samples from a subdistribution of the target distribution at each step. Because a subdistribution contains less information, the sampling result may not be satisfactory in one single step. However, the power of subsamplers lies in their ability to be combined. Since subdistributions are compatible with the target distribution, multiple subsamplers can be used in sequence to progressively refine the sampling result and converge towards the desired distribution. The simplest form of subsampler is the basic sampling process, which samples one token at a time. However, more sophisticated subsamplers exist, such as speculative sampling. By breaking down the complex target distribution into simpler subdistributions, subsamplers provide a modular and flexible approach to sampling. We provide rigorous theoretical guarantees for the convergence of tree Monte Carlo methods based on subsamplers. Some additional conditions are included, such as the leaf-only property, which is technical, and non-degeneracy condition, which is essential. We can prove exponential convergence, but this convergence in terms of total variation distance cannot be easily demonstrated since the definition of the tree distribution is too general, which may contain infinite details. If we consider a looser notation of convergence such as pointwise convergence, we can indeed prove exponential convergence similar to conventional Monte Carlo methods. In summary, based on the concept of subsamplers, we provide strong convergence guarantees for tree Monte Carlo methods. Finally, we can talk about accelerated speculative sampling. Although the actual algorithm is quite complex, the underlying idea is simple and intuitive. The basic idea behind accelerated speculative sampling is that we tweak the joint distribution to achieve better coupling on the tree space. One special example is shown in previous slides. We also need to respect the neighbor structure on the tree space to make sure the algorithm is indeed a subsampler. The soundness of this approach is guaranteed by the property of subsamplers. Moreover, accelerated speculative sampling has a higher or equal efficiency compared to conventional speculative sampling. Here are some experimental results. Accelerated speculative sampling demonstrates higher efficiency compared to conventional speculative sampling without compromising the output quality. The actual amount of acceleration depends on factors such as model, the length of the draft tokens, and the specific task. In conclusion, by leveraging the tree structure of the generative space and introducing the concept of subsamplers, we have developed a novel and powerful approach to accelerate the inference of large language models. This not only provides a solid theoretical foundation, but also yields practical improvement in efficiency. Thank you.